Okay, a couple of administrative things first. Today we're going to finish up 2.1, and the material on 2.1 will be on the exam. That is on Tuesday. We'll also start 2.2, and I'm not going to put that information on the exam unless perhaps I want to put it on there as a bonus question. All right? Now that doesn't mean like completely shut me off like once we get to 2.2. I mean, pay attention, but just be assured that you won't have to be cramming that homework assignment in before the test. Yes?
So is it everything leading up to 2.1?
Everything we've done up to 2.1. And I'll talk a little bit more about the exam at the end, but I would not expect to have some like full-blown 30-minute session on, talking about what's going to be on the exam. It's going to be 5 minutes at the end, and I'm not going to hand you anything, but we'll talk about that when we get to it. Also, it has been brought to my attention that my homework solution videos, when I made those, which I made those a couple of years ago, YouTube used to allow me to do what were called annotations, which means like during the video I could like make a little box pop up and it would say like, hey, oops, I made a mistake, like that's supposed to be a negative, whatever. And then you would see it pop up and then it would disappear. And then they told all the YouTube people, they said, look, those annotations, you can't make them anymore. I said, okay, and then they said the ones that are there, we're going to keep them there for a year or so. And I guess now they're all gone, okay? So there are errors in my homework solution videos that used to be noted, now they're not. And then there's some that I think some students have caught that weren't caught before. So long story short, if you find something in a homework video that just looks off, bring it to my attention, and I'll give you bonus points for that. Okay, so if you find errors in the videos. Now, if someone else has already found them, you don't get bonus points, all right? So we've found like what, 3 or 4 of them already? So in the first few videos. Was it 5 of them? I thought some of them were the same though. Yeah, some of them were the same. So anyways, just be aware of that, okay? All right. Now, we need to pick up with where we left off last class. And the main thing we left with was that if you're given a function, then we can calculate this thing called the derivative of the function at a. And that derivative you can find by using one of the two formulas. And I said, you're kind of going to pick the one you like, and I've been told that on my homework videos I seem to use this one a lot. Okay, there's a kind of a reason I use this one more, but we're going to see that in 2.2. So here's a problem I've put up on the board for us to start, because I really want to make sure we have 2.1 kind of fully understood. We have a function, and part A is asking you for the derivative of the function at 0, part B, the derivative at 2, derivative at -4, derivative at 7, derivative at -1. So if we do what we did last class, what we would have to do is we'd have to set up that limit for each of these problems, right? For all 5 of these, we would have to do a limit, right? And that would take a while, wouldn't it? That would take a while. So instead, what we're going to do is we're going to try and figure out if we can find a formula for the derivative at a. Okay, so I'm not going to want to look at all 5 of these. Instead, I'm going to say, can I find a formula for the derivative at some arbitrary point a? And then if I can come up with a formula for this, then all I will have to do to answer these questions is just replace a with 0, 2, -4, 7, -1, and that will go quick. So this might be harder to do in terms of the algebra because you don't have really numbers in there. You're just going to have a bunch of letters. But the payoff is that we can wipe through these real quick once we have this. All right? So that's what I'm going to do to start this. So let's find f prime of a. And I'm going to use the limit as h goes to 0 of f of a plus h minus f of a all over h. That's the one I'm going to choose to use here. All right, so I need to set up that limit. I need to let h go to 0 and see what I get. But I'm going to be using this function, right? Okay, so let's go ahead and start plugging things in. This limit now becomes the limit as h approaches 0. All right, let's talk about that top left corner, f of a plus h. This right here is what I get when I plug a plus h in here and in here, right? I'm going to replace both of those x's with a plus h's. And so it's going to look ugly, but this is what it is, okay? It's 3 parentheses a plus h. What else on top? Minus 1 still. And then over, what? A plus h plus 2. Okay, that is just that top left corner, right? That's just that. And now I need to, any questions on that? Okay, now I need to subtract from that f of a, right? And I'm not plugging in a number, I'm just going to leave it as a. So that means I'm going to replace that with a and that with a. So that's going to be minus 3a minus 1 over a plus 2. We still on board? All of that over h. So we have this expression here, this right here, oh, sorry, is this piece right here, right? And then all of it over h. We good? No? Yes? What?
Where's the a plus h plus 2 from?
Where's this come from?
Yeah.
This one? I'm replacing x with a plus h.
Oh, okay.
So it's just a plus h, then plus 2. Okay. All right, now we have what we refer to as a complex fraction. All right, it's fractions within fractions. And so anytime I see a fraction up here, two fractions, I'm going to try and put them together and try and get a common denominator. All right, and this part's going to be messy. It's going to be real messy. So our common denominator is actually like this denominator here and this denominator here. I need to have this a plus 2 next to this here on the top and the bottom, and I need a plus h plus 2 on the top and the bottom here. Okay? Some students, and this is a huge mistake, all right, so don't do this on a test. Some students think that they just need to do like a plus h here and a plus h here, something like that, because this already has a plus 2, right? So all you're missing is plus h, but you can't do this. The reason you can't do that is because, like, if you take any fraction, 3/4, if I add a number on the top and add a number on the bottom, is it the same fraction? No, it's now 4/5. And 3/4 and 4/5 aren't the same. Now, could I multiply by 1 over 1? Yes, but I can't add top and bottom. Make sense? So that means we have to take this big hunk of crap right here and put it here and here, and then that one right there, he put it here and here. Here we go. Limit. H is approaching 0. All right, I'm going to do a plus 2 over a plus 2 times 3 times a plus h minus 1 over a plus h plus 2 minus 3a minus 1 over a plus 2, but then times that big old nasty thing, a plus h plus 2 all over a plus h plus 2. Understand? That's what I'm going to do for my common denominator. Now let's try and work this out. Notice my limit, right? I keep saying this to you. I'm not getting rid of my limit ever. And in your work, your limit should be there the whole time until you get to the very end when you let h go to 0. All right, so let's try and clean this up. I'm going to be multiplying this times this, right? Now I'm going to clean this up a little bit. I'm going to distribute the 3 through real quick. And that would have been 3a plus 3h minus 1. So that's really what I have up top there, right? That's what this is. And then I have to expand that out. I have to multiply that out. I have no choice. So let's do it. What would you get when you multiply here to here? 3a squared. So that's going to go here. And then here. Plus 3ah. Does it matter if I put ah or ha?
No.
It doesn't, right? Because it's multiplication. Then here, minus a. And then now we go to the inside. Here to here, plus 6a. Plus 6h minus 2. That's the numerator of this one, right? And that's all over the common denominator, which is a plus 2 times a plus h plus 2. Okay, so notice I'm not multiplying these together. I don't recommend you do that either, okay, because ultimately what we're trying to get at the end of the day is for a single h to cancel, right? This h to cancel. And the only way that's going to cancel is if something up in the numerator cancels. What's down here doesn't matter. So remember, this is all going to be when I'm done over h, right? So all I've done is this. Now I need to go minus, and then I got to put this together. I can't help but sit here and think to myself that maybe you're sitting there going like, wow, this is my reality. Like, this is what I have to do, you know, like. And yes, it is. This is your reality now. This is what you signed up for.
The way you say it sets me up to think, and here I am thinking he must be waiting for the perfect time to tell us that there's some trick that he's gonna.
It's going to get easier. I mean, I should say this. There's going to be shortcuts, okay? I'm going to give you shortcuts that are going to make a problem like this much easier to do. But there's going to be a trade-off. If
Shortcuts, you have to understand.
we do. But the thing is, once we get the shortcuts, what happens next is then the functions become more complicated. So there's a trade-off. Like, yeah, we'll have shortcuts, but now let's try some crazy-looking functions. Yes?
Yeah, is it okay if we could use the other formula, though? I know it'll take longer, but...
Yes, I mean, you can. You can. Okay, am I done distributing? Oh, no, I'm not. Shoot, I still have more to go. Sorry, I got distracted. Okay, so here to here, so minus a, and then minus h, minus 2, and that's all over the same common denominator, a plus 2 times a plus h plus 2. And now that's it, right? So now we can put these two together, right, into one fraction because they have the same denominator. Just be really careful here because that minus sign has to pass through the entire numerator here, which means every sign up here is going to change. Yeah, let's do it. Let's see, I'm going to put that right here. Probably need a bigger line. Let me get all this out of here. Some of your classmates that I met with in my office today mentioned that these problems are taking a little while to do and that it's taking up quite a bit of space on the page. And my response is, yeah, that is what you should expect. Bless you. Okay, all I've done is rewritten that numerator, and then now I'm going to go ahead and take the minus and distribute it through. Now I'm already sitting here thinking here that if I did this correctly, then when I'm done canceling everything here, I should have things that have just h's in them. Like that should happen. We're going to have to wait to see. Okay, that's all of this over the common denominator. And then all of that over h, right? Little side note here. Side note. What's 12 divided by 6 divided by 3? What is that?
Well, that's 12 over 6 times 3 over 1.
So I think there's two ways to look at this. This could be 2 over 3, which would be 2/3, right? Or you could look at that as a 2, right? And then go 12 divided by 2, which would be 6, right? So by me writing it this way, it's hard to see which way to go, right? So it's important that if we ever write something like this, we make one of these division bars longer than the other one. And what that does is it says, okay, here, this division is where we split the line. So we do the 12 over 6 first, and then we do divide by 3. Now I could have done it this way, and then we get a different answer. Does that make sense? So when I'm drawing this division bar right here, my next division bar is actually longer than this one. Does that make sense? And then this is like your h down here. So we got to do like, all that and then divide by h. This is just a side note, just FYI. These division bars, their lengths actually matter if you write fractions over fractions. All right, do we get good cancellation?
Yeah, the 3a squared.
3a squared's gone. 2's are gone.
And then negative a.
Let's see, I have an a here, 6a, 6a,
It doesn't have an h attached to it.
3ah cancels. Is that it? That's everything that cancels, right? So all you're left with is 7 h's on top. And if everything worked out the way it's supposed to work out, whatever's on top should have at least a factor, like one factor of h in whatever's left. So it's actually really nice. It's limit h goes to 0. All I have is 7h on top. Then I have the common denominator, a plus 2 times a plus h plus 2, and then all of that over the h. Y'all with me on that? Okay, now what? You can cancel the h's, right? This h and this h cancel. And just remember, the reason why is really because that's like h over 1. And then you could flip this fraction up and make it a 1 over h. And then the h's would cancel. Okay, but I'm just going to cancel it like that. So I think we're one step away. Limit, h goes to 0. I'm just rewriting it first. 7 over a plus 2 times a plus h plus 2. There we go. There it is. Now, finally, we let h go to 0. And if h goes to 0, this guy right here is the only one that has h, right? So that's going to go to 0. So what you wind up getting is 7 over a plus 2 times a plus 2 again, right? So we could look at that as being 7 over the quantity a plus 2 squared. And this is the derivative of our function at a. So if you would like to look at that graph, what was it? F of x was, I forgot, 3x minus 1 over x plus 2. If you graph this, if you would like to know the slope of the tangent line at some given x value, then all you have to do is replace that x value with this number. Replace that x value into this formula, and that will give you the slope of the tangent line. So now we can answer all 5 of those questions pretty quickly, can't we? Let's see. Let's answer the question. What was the first one I asked? What's f prime of 0, right? So what would f prime of 0 be? Well, that means we just plug 0 into this formula, right? For a. So we get 7 over 2 squared, so 7/4. What was the next one I asked? 2. So now we plug 2 into this formula. So 2 plus 2 is 4, squared is 16, so 7/16. Next one, what did I ask? Negative something? Negative 4. So be careful there. If I plug in negative 4, what do I get? So negative 4, that's negative 2 squared 4. So 7/4 again, right? And what else did I ask? 7. F prime of 7 would be 7 over 9 squared, right? 7 in there, so 9 squared, 81. And then finally, to ask for negative 1. So what would we get at negative 1? We just get 7. 7 over 1. See, and now I could do this all day long, right? I have a formula now. So if someone needed to know the derivative at like 30 different points, I don't have to go through and do the limit 30 times. Yes, I had to work pretty hard for it, but now I've got a formula, right?
You can liken this to reality in the sense that you work your hardest or strive to create something stretch apart. Basically, you just work really hard in the beginning of your early life, so that way you can have a cozy life later on.
That would be a good plan.
I have an idea.
Yes.
Why don't we do those x's and then see
Cube the x's in, yeah, no thank you. The suggestion was to do like 3x cubed minus 1, and yeah. And then that's when we would say, yeah, those shortcuts are going to be worth it. So once we get the shortcuts, we'll come back and do that. Okay. So I think that's it for 2.1. Let me just make sure, let me look at the notes here. We'll kind of do a real quick little summary. We've got the derivative, right? The derivative function at a. Remember also that we look at the derivative as a slope, but we also can look at it as an instantaneous rate of change, or if the curve we're looking at is linear displacement, so an object moving in a straight line, then the derivative represents the velocity at a specific instant in time. Now we move on to the next section, 2.2, the derivative as a function. All right. So we just saw that when we're given a function, we can calculate f prime of a and not plug in a specific number for a, right? We just did that example. And what we got was a formula, right? In the last problem, it was 7 over, a plus 2 squared. That's what we got. But a, I could have used b here, right? I could have used c. I could have used any dummy variable I wanted in there. We used a. But if we replace a with x, because it's a variable, then we can actually look at the derivative as being a function, just like the function, we started with a function, didn't we? And the derivative, if it's a formula, is actually a function also. So the previous problem, I gave us this function. F of x is 3x minus 1 over x plus 2, right? And then when we took the derivative, we got f prime, and we used a here, right? But I'm going to just replace that with x, and then it would have been 7 over x plus 2 squared, right? Like that? Or was it minus 2? Plus 2, right? So this is basically the formula we just came up with, but I'm replacing a with x. So wipe your brains for a second and just imagine you walk into class right now and I put this on the board. Would everyone agree that you would have just thought, okay, that's a function? It has a graph, right? And that's what we're looking at right now, is that if we start with a function, it has a graph, right? But its derivative is actually another graph. And they're somehow related to one another. If we look at them, there's one, we can look at this one and actually get an idea of what this one looks like. And that's what we're gonna try and do right now. So here we go. Here is a function, all right? This red function kind of looks a little bit like a sine curve, right? What I've done is I've picked some arbitrary point. So I'm going to some value here, and I'm going to go down to the function, and then at that point, I'm finding the slope of the tangent line. So I'm having the computer calculate the derivative for me. And over here, where is it? Oh, over here, it's actually spitting out the value. So do you see that it's green and it says 2.1? Yes? That means the slope of this tangent line right here is 2.1. Now, if I move this point to the left a little bit, what's going to happen to that slope? Is this number going to get bigger, smaller, what? If I move to the left a little bit, smaller? So let's try. Let's move it to the left. See what's happening. Do you see this? Do you see the slope of this tangent line is actually becoming more flattened out? And remember, horizontal line has a slope of 0. Diagonal, perfect 45 degrees, has a slope of 1. And then the steeper you get, the bigger the number. And then, of course, if we go this way, it's just the same thing but negative. So we've got a positive slope here, right? So now, what if I were to plot that answer? So imagine taking the answer here, which is 1.4, and plotting it as a point. Let me do it here. Right? So I'm taking the slope of the line right here. That answer is 1.4, and then I'm kind of starting over with a new graph, and I'm saying, look, if I'm at this x value, I'm going to be plotting its slope, and the slope is 1.4. With me? So if I move to the right now, what would happen to that green dot? It's going to start moving up, right? Because the slope is getting steeper. Now, what's going to happen when I get about right here? Like, it's going to keep going up, but then what's going to happen? Right about here, why is it coming down? Why is that point coming down? Because this slope is starting to flatten, right? It's still positive, but it's getting smaller. So that number is getting smaller. Do y'all see the connection? And then what would happen when I get right here to the middle of this graph? The slope is going to be 0, which means that point needs to come down and be 0, right? See that? And then when I go this way, what's happening? My slope is negative, right? So the point that I'm plotting is negative. And it's eventually going to go down. And then what's going to start happening now to that point? It was going down, right? Now what's going to happen to it? Right about in here. It's going to start coming back up. Because this tangent line is negative, but as I come down to here, it starts to flatten out again, right? So it's still negative, but it's smaller. So this is a negative number, but it needs to be smaller, so it needs to move up towards the x-axis. So it's going to go like that. Okay, now let me just back everything up all the way. And now let me actually show you all those points together. Okay? The green is the graph of the derivative of the red one. So the red one is the function we start with. The green one is the graph of its derivative. So it's essential that you see that if I just come in here and like grab a point, you know, just like, okay, right there, I'm going to say to myself, okay, I should have a positive number, right? And that means on the derivative I should be positive. If I were to go over here, I can say to myself, okay, I know the slope is negative, so my derivative should somehow be negative. Yes? Do y'all see the relationship? We're going to look at a couple of other ones now.
That negative of the green,
What's that?
like you said it was positive on
No, right here, if I pick a point on the red graph, right? If I pick this x-coordinate and come down to here, my slope is negative, right?
but on the other one though, it's going up. And
Right here?
And the green one's going down. Yeah.
Okay, so right here, if I pick a point, right?
Yep.
What's the slope of that line?
It's positive.
Positive, which means that the green function better be positive. Positive means above the x-axis,
Oh, yeah.
right? Positive, we're not looking at this, for the green one, we're not looking at its slope. We're looking at whether or not it is above or below the x-axis. Positive or negative, positive or negative.
So you can kind of use that to double check that your derivative is done correctly.
Yeah. Let's look at this one. You know what? I think we should not start with this one. I think we should start with this one. All right. So let's pick a point. Pick an x value. Ready? Tell me when. Okay, right there. I'm going to pick an x value. I'm going to go down to the function. I'm going to grab a point there. And now the tangent line is actually that slope right there, isn't it? And I'm not quite sure what it is other than to say it's positive. Agreed? Now, if I pick some other point, right? Go, what's the slope of the tangent line there? Still positive. But this looks like a line, doesn't it? So isn't the slope here the same as the slope here? In fact, if I pick any value off this graph, the slope is going to be the same at every point, which means the derivative, the value should be the same the whole time. It should be positive, and it should always stay the same. So the derivative of this, if we graph it, should be a flat line. Let's see it happen. Take these out here. So I'm having the computer right now go through and graph the derivative as I move. Do y'all see that? The derivative is always staying the same as I move across. Now, this function was the function 3x, and it turns out that the derivative of that is always 3. Let's look at x squared. So I'm going to try and do this one by hand. Let's use the sticks. We haven't used the sticks in a while. Alberto.
Yes.
All right, so Alberto, I'm going to pick a point for you right here, and you just tell me whether or not that the derivative is positive or negative there. It's what? No, you're right. I just want to make sure everyone hears it. It's negative, right? The slope of the tangent line is negative. So that means if I'm trying to graph its derivative, which I do have some green here, then I just need to put a point like somewhere in the like below the x-axis, right? So like I know that the derivative is going to be somewhere around here. Okay, I'm just kind of guessing. This is kind of a guesstimate. Now, Aaron, where's Aaron? Aaron? James? All right, James, I'm going to pick another point, okay? So here's the point I'm picking, right there. So is the slope of the tangent line there positive or negative? Negative. Negative, okay. Now, that means I need to put a point down here, right? Can you tell me whether or not the point I put down here should be like the same as this one, maybe a little lower, a little higher?
It should be higher.
It should be higher. Because the pitch of this line is steeper than it is here, right? Steeper slope means bigger number. Bigger meaning negative. So this has less steep, and therefore the number is smaller. It's still negative though. So I would think it would be somewhere, I don't know, I'm just going to guess again right here. All right, who's next? Tatum, you're next. How about here? Is my slope positive or negative? Negative, okay. So is that point going to be, the negative point, is it going to be same as this? Higher or lower? Higher again, right? So it's getting closer. This derivative is getting closer and closer to trying to get flattened out to 0, right? So when I get to right here, Brian, what's the point for my derivative there, Brian? Right, this point right here. 0, right? Which means I need to put a green dot at 0, which it's actually right on top of it, isn't it? It's right there. Okay? Rasul? Here's your point. I need a green point. I'm going to put a green point that represents the slope of the line there. Where's it going to be? Positive, right? So just put it, anywhere above, right? And then, who's next? Well, we're going to get through everyone like this. Marissa? Where's Marissa? Okay, you get this point right here. So where do I put the green dot for the derivative there? Anywhere above. So because it's positive slope, it's going to be anywhere above. Now, relative to this point, should that point be down here or up here or the same? Higher, right? Because it's steeper. Bigger number goes higher. So I'm going to put it like in here, all right? So you kind of start to see what the derivative looks like. Yes?
Do you know what point it's going to cross?
What point that it's going to cross where?
Like, if you drew a line connecting the green dot, it's going to cross the function. So how do you know where?
Well, that actually is not something we'll ask ourselves. But to answer the question, if you wanted to know where the derivative hit the original function, like where they intersected, you would have to take both the functions and then set them equal to each other. Now, we're not going to do that, but that's what you would do. The important thing for us right now is to see that if someone gives us a graph, can we sketch its derivative? Can we? So y'all ready to see it? This is the computer doing it for us. Oh, I should show it, huh? I'm not showing it. There it is. Here it comes. Negative values, very steep, going through 0 and then growing, right? There it is. So, I mean, we weren't perfect, but we were guessing, right? Yes?
So on that side is negative?
Pardon?
Yeah, on that side?
Yep.
You said it has to go
If we're over here, it's very steep, right? But pointed down. Down means negative. So a very steep negative number would be a very big negative number, which is why these points are way down here. These are big negative numbers down there, right? And as I go to the left, it would just get steeper and steeper. So these numbers would just keep getting bigger negative Yes.
So to clarify, as the slope points down, it's negative, right? If it points up, it's positive.
That's exactly right. If you're moving from left to right, if you're going down, remember we had this idea of decreasing and increasing? We talked about this like on the first day of class. You have functions and we talk about where they're increasing and decreasing. If your function is decreasing, you know the derivative has to be negative there. If the function is increasing, you know the derivative has to be positive. Anywhere where it flattens out, you have 0. Let's look at another function. Let me back this thing out. Take a second to look at that. Don't say anything because I'm going to ask some lucky person here is going to get a good question now. Is that enough time? Good. Okay. Savannah. Where's Savannah? How? Sorry, you got picked. Savannah. The derivative of this function, if you pick points, it looks like the derivative is really almost always going to be what? Like if I pick a point here and go right here and ask you, is it positive or negative? What are you going to say? Positive. But if I pick something over here and ask you, what is it going to be? Is it the derivative? It's still positive, right? The function's negative, but the derivative is still positive. Do you all agree? And it looks like almost everywhere I go on this graph, almost everywhere I go. Like pick a point here, positive, right? Pick a point here, positive, positive, positive. Now it does flatten out to 0, right? But then as soon as it gets past this, it goes back to being positive, 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 positive again, right? So I should have positive numbers over here, right? Big positive numbers. And then I should stay positive, but get closer to 0. So imagine, big positive numbers, as I move this way, those positive numbers get closer to 0. And then when I go over here, small positive, getting bigger. So it's going to go big positive down to small positive to 0, and then small positive up to big positives. It's going to look like a parabola. There it is. Brian, you're giving a look like.
I got it.
You sure?
But that's not.
This is a light bulb. This is one of those light bulb things. You see it, it's good. You don't see it, it's a disaster.
So if the red line is like opposite, well, it'll be negative, right? Negative, negative.
If the red was what?
Like, flipped.
If it was down here,
Yeah.
then this green couldn't be up here. Because if the red came down like this, we would have negative slopes, which would force our green one to be below the x-axis. The reason that the green is above the x-axis almost the entire time is because our graph is always increasing, so we always have positive slope. Unless we get to this point. At this point we have 0. So very steep, flattens out, 0, and then shallow back to steep. Yes?
So for the green one, it doesn't matter whether it's going down. You know how it goes
No,
down, it's
I'm not asking you for the slope of the tangent line here.
positive or negative.
It's whether or not it's positive or negative. So we're just worried about, is it positive or negative, and then how big, positive or negative. That is also important. Like if you're here, very steep, very big number. You're here, not as steep, smaller number. I have a few more to look at. I have 3 more to look at. Yes?
So what we need to understand is kind of like just be able to like sketch it, not necessarily know the numbers of it.
That's right. You don't need to know the numbers. So what I'll do is I'll give you a picture and then you draw me the derivative. And everyone's is going to be a little different. Like it's not going to be precise. Like every point doesn't matter. It's the general shape. Like you can't have your green drawn on top when it's supposed to be on the bottom.
Are we going to get precise with the formulas?
Are you going to get what?
More precise with the formulas?
Yeah, once we have the actual formulas, we can find them. Yes.
Do derivatives also follow the same restrictions applied by asymptotes?
So if you have an asymptote in the original function, will your derivative have an asymptote?
Yeah,
Is that what you're asking?
Will it follow the same restrictions as as in it can't cross that asymptote, or is it able to?
Yeah, that's an excellent question. So every function has an implied domain, right? Things you can and cannot plug in. The domain of the original function carries into the derivative. Okay, so the domain of the derivative is also still the same as the domain of the original function.
So then in this case, we'll have two derivatives?
We're going to have a derivative that has a piece missing, is what's going to happen. So take a second to look at this. All right? All right, so let's start with this. I'm going to move from left to right, and you just tell me whether or not my derivative is positive or negative. Ready? Here. Negative, 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 right? So the whole left side, we have a negative derivative. Now, come over here. What do we have? Derivative is negative, 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 right? So that's the first thing. We know that when we draw our derivative, it's always going to be down here. Yes? Okay, now let's talk about steepness. Not very steep, right? So small negative number. I'm going to do it in red. No, I better not do it in red. Small negative number. That small negative number? Over here. It's still small, but a little bit bigger than this, right? So maybe a little bit below. I'm exaggerating so you can see it, right? Then I come over here. What? Still negative, right? But steeper, so bigger. Over here? Down here, right? Little dot down there. So can you kind of get a feel for what the derivative's doing? Something like that? Okay, now over here. Maybe let's start this way and move backwards. So over here, here's my tangent line. It's negative, we knew that, but it's small. Over here, still negative, but a little more steepness to it, so bigger. And then here, steeper, more negative. And then here, there. So I'm thinking something like that. There it is. Yes? Yes.
So on that one, you read it from left to right.
Mm-hmm.
And when you read it from left to right, it's obvious that it's a negative derivative.
Mhm.
Then when you were drawing the derivative itself, you went right to left.
Yes.
So how do you know, if you're going from right to left, how do you know it's still negative and not positive?
Because our definition of slope is rise over run. So if I'm moving, imagine I'm moving from this point to this point, right? My rise is this, right? So my rise is actually negative, and my run is positive. So negative over positive would be negative. Now if you reverse and go the other direction, now my run is what? Negative, and my rise is positive, and the ratio is still negative. So it doesn't actually matter which way you go about it. Does that make sense? Okay. Good question. Good question. All right, next one. Was there a question? Oh, sorry, I didn't. Ignore the red. It's freaking out. I'm not sure why it's freaking out. All right, what?
Can you actually go back?
Go back to that one? Oh, yes. Uh-huh.
So when you drew the green line,
Yep.
so when you drew the points on the left side
Yep.
for the negative, you were below the red line?
No, that doesn't matter.
Does it matter?
That doesn't matter. That's what I'm saying. We don't have to be that precise. Okay? We don't, on your test or quiz, what I'd want to see is, that's what I want to see. Okay? That's your question also? Okay. We're just trying to get what you could look at as we want the behavior of the derivative. Okay, it's behavior. Yeah, let me move this x. I'm not sure why. Oh, because my domain. All right, that's why. Okay, let's talk about this one. So my function is the square root function, square root of x. And so let's just first talk about positive or negative. So slope of my tangent line here, positive, 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 right? There is no graph here because the root function is not defined over here. So I'm going to have positive. My derivative is always positive, isn't it? Okay, let's talk about the steepness. Here, I'm a positive number, right? I'm what kind of, that's steep, I guess, kind of steep. So a positive number somewhere. But as I move to the right, what happens to that steepness? It starts to kind of flatten out, right? So these positive numbers are going to start getting smaller, aren't they? Now this, as I go out, continues to try to flatten out. It never truly flattens out, but it tries to. So what is it approaching? It's trying to approach flatness, which is 0. So my derivative should always be positive, as I move to the right, should always be above, but it should be getting closer and closer to 0. So that means I'm going to have, like, my dots are going to be like, okay, I was here, and then as I moved over, I'm still positive but smaller, still positive, smaller, 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 and I'm going to, like, have an asymptote. It's going to be approaching 0. These are all positive numbers, right? Now, the more interesting question is what's happening right here. I'm going to have to back this out. Just ignore that the computer freaked out there for a second. What's happening as I try and get to here? So look at the line, look at the steepness. As I try and make that turn, what happens? I'm starting to get steep, right, like this. And you're trying to actually come in there, and you're trying to become vertical, right? Your derivative is trying to become vertical. Now remember, as we move in like this, that's getting steeper, which means bigger positive numbers, right? But vertical lines, the slope of a vertical line is undefined. It's like having division by 0. But do you agree that as I move to the left, these numbers are getting bigger and positive? So what we wind up having is a vertical asymptote like that. You can never get to that point, okay? You can actually never get to the end point, because if you get there, your slope of your tangent line will be undefined. And so that's what the derivative should look like. Here it comes. No, there it is. Make sense? Yes?
So as you're saying that, like it gets steeper, and so it's a bigger positive number.
That means a bigger positive number.
The X or the Y? Or what do you mean by like
This point right here, right?
Yeah.
The y coordinate of that point is positive, and it's kind of big. But as I move closer this way to the left, I'm going to have a bigger positive number.
as you
No, to the left. Look at the derivative. Here's my slope of my tangent line, right? These are getting steeper. See, I'm trying to come around that turn. See, that's like a little curve there. So I'm trying to come around, and so my line is starting to want to get steeper. Steeper means bigger, positive number here. So I'm trying to get bigger and positive. The derivative must grow. What's that?
You're going down.
I'm not going,
Or you're not.
well, don't look at me as going down or up. Look at it as the steepness of the line. Right? So my tangent line is getting steeper, right? If I move to the right, it gets more shallow, and therefore it's smaller slope. 0 slope, slope of 1, slope of 2, 3, 4, 5, 6, 7, 8. This is like, slope of 30. You can't get vertical though. Vertical is basically infinity for a slope. Okay, let's look at another one. Good old sine function. All right, let's move here from left to right. You just tell me whether or not the derivative is positive or negative. 0, so I'm tricking you. So that means I should have a dot like here, right? Now, tell me about my derivative, positive or negative? Negative, 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 0. Now what? Positive, 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 still positive, still positive, still positive, 0 again. And then negative, 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 negative. And then when we get to here, 0. Right? So now let's talk about the steepness. Yes?
So, since the sine wave
would also apply to if this was a cosine wave?
Yeah, if this was cosine, we could do a similar thing.
So then could you say that at every min and max point, it is 0?
For a sine and a cosine wave, yes. At every top or bottom of a wave for sine and cosine, the derivative is 0. Exactly, you could say that. Something really interesting is about to happen though. Okay, so we already talked about positive, negative, right? Let's talk about like how big, okay? So we already said here was 0, here you said this was negative, right? And small. And then it's going to get negative bigger, 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 smaller, 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 smaller. So I'm going to go 0. These are all going to be negative numbers. Small, 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 right, sorry, small, but getting bigger, getting bigger, getting bigger. When I get to here, it kind of starts to turn back and starts to get smaller. So I'm going to have 0. I'm going to have negative numbers that get bigger, 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 bigger. And then when I get to here, they have to start getting smaller, 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 and come back to 0. Right? Now, once I'm here, what's going to happen as I move to the right? Positive, right? But small, small, but getting bigger. And then once we get to here, we're still positive, but we've hit kind of like a maximum pitch of our line. And then we're going to start to flatten out again and go back to 0. So it's going to look like this. And then, same thing over here. Do y'all kind of see that? Now let me do the computer. Let me let the computer do it. The computer's is a little nicer. I'm going to take mine out of here. Does the green function look familiar? It is the cosine wave.
Or a sine wave that's been shifted.
Or a shifted sine. But it turns out, we're not ready for it yet, but it turns out that if someone asks you for the derivative of the sine function, it's cosine. So remember, I started class with 3x minus 1 over x plus 2, right? And we found its derivative. And if we look at that as a function, it's a new function, right? We could graph it and everything. If you take the sine function and you want to graph its derivative, it's the cosine function. Kind of interesting. Okay, so let me ask you this now. If I'm telling you right now that this is the cosine function, I'm telling you that right now, then can you tell me what the slope of the tangent line is right there? On the red one. Here's the red curve. What's the slope of the tangent line there? At the origin, what's the slope of this line? 1. Where'd you get that? Who said that? The green. Yeah, the green one, right? So if I want to know the steepness of this, I just have to go to the green graph and pick off how high that is. And if that's the cosine function, then the highest point is 1. So the slope of that line right there is 1. Make sense? What's the slope? What's the slope of the tangent line to the red one right there? -1. Because the cosine is -1 here. The green one is the cosine. Is cosine x.
Oh, yes.
All right, let's proceed. See if there's some other ones I want to look at. No, okay.
Is the opposite also true?
Is what?
Is the opposite also true as in like,
Is the derivative of cosine sine? Why don't we answer that question? So we just saw that the derivative of sine was cosine, right? I think I maybe convinced you. But the question is, what is the derivative of cosine? So I'm going to see if we can't do it by just graphing it. So are we all familiar with the idea that this is one period of cosine? That's cosine x. Help me out now. Let's draw its derivative. All right, so let's start with the points that are easy. What's the slope of the tangent line here? 0. So I know the derivative is 0 here, right? What's the slope of the tangent line here? 0 again, so I know I've got that, right? And the only other place that looks like that happens is here, right? So that's those 3 points, the derivative is 0. Now tell me what's happening here as I move to the right. Negative, small. Negative getting a little bigger. Negative getting bigger, right? And then we get to some point here where we have to start tilting back, right? So we're going to have negative small, and it's going to get bigger, and then it's going to go back to 0, right? So something like this. And then when we go from here to here, it's going to be positives, right? And then go positives back to 0. So it's going to look like this. So the question was, we just saw in the previous problem that the derivative of sine of x appears to be cosine of x. The question was, is the derivative of cosine x sine x? Well, is the purple sine x? Not quite. It's actually negative sine x. It's sine x flipped over, isn't it? Because sine looks like this. So if you flip that over, you get this one. So this is something you will have to memorize later. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. And there will be a bunch more. You have to know what the derivatives are for all the trig functions. Sine, cosine, tangent, cotangent, cosecant, secant, all of them you have to have. Like, we need to know them. All right. Now, oh, I did want to do another example. Here's the function that I want us to graph the derivative of. Take a moment to draw this properly. Oh, okay. It's supposed to be a straight line. It's the W function. What does its derivative look like? Okay, so this right here is our function, f of x. I would like to know what its derivative looks like. Okay, so how do you mean? So tell me about what's happening at this point right here. What's my slope, positive or negative?
Negative.
Negative, right?
Yeah.
And as I move to any point here, it's always negative, but it's the same, right? This is not changing pitch. So I'm going to have a negative number, it's going to stay the same the whole time. So let me try and draw that. I'm going to do it in red. So you said I'm a negative number. Do we actually know what the value is? Do you know the slope of this little piece? So it looks like I go down 2 over 1, right? So that actually has a slope of negative 2. So if I want to be really technical, I could go down, here's 1, here's 2, here's negative 2. I know that it's going to be exactly negative 2, like that. Does that make sense? Negative 2, the whole time the derivative is negative 2, negative 2, negative 2, and then something crazy happens right here. What happens at 1, at negative 1? It's going to, like, all of a sudden, our derivative is going to go from negative 2 to a positive. And this has a slope of 1, 2, up 1 over 2, so the slope is still 2, but now it's positive. Y'all get that? So that means it's positive 2, and it stays that right here. Do y'all see? Negative 2, negative 2, negative 2, negative 2, and then something, the universe collapses for a second, and then we go positive 2. And there's a jump from here to here, isn't there? Our picture has a huge jump in it. And right here, we're going to have to kind of leave this as an open question, like what's happening at negative 1? Like what the hell happens, right? I'm going to leave them as open circles for now. But something crazy happens at this corner.